Okay, last part of chapter 8. We are talking about the attractions that occur between molecules. Now that we understand the polarity of molecules, we know that there are some molecules that are going to have those partial positive and partial negative ends, and they can act a little bit like a regular ion. You know, a regular ion has a full positive or a full negative, and they attract because opposites attract. Well, if there's partial positives and partial negatives, you get the same kind of thing, although not as strong. So if you have one end of the molecule that's more negative and the other end is more positive, then you technically have two poles. We call that a dipole. And any molecules that have these poles can then somewhat act like ions, and they can attract the opposite charges around them. So for example, here's my molecule, okay? It's really simple. I don't even put any actual, Lewis structure there. I just wanted you to recognize that we've got partial positive on one end, we've got partial negative on the other end. Well, let's say there's another one of these exact same molecules nearby. Well, what's going to happen? This partial positive end is going to be attracted to this partial negative end. And then if there's another molecule of the same kind around and another molecule and so on and so forth, there's going to be constant attractions between the partial positive and the partial negative ends, right? And that's going to hold these molecules together. Again, it's not as strong as an ionic bond. Ionic bond is full positives and full negatives holding together, right? Ionic compounds are really strong because of that. These are more attractions instead of full bonds, because we're talking about partial positives and partial negatives. So there's a difference here. We're not talking about intramolecular forces. That's the forces that occur within the molecule. That would be the actual bonds, like covalent bonds and ionic bonds. What we're talking about here is intermolecular. Inter means between. These are the forces that occur between the molecules. Now, technically, ionic can still happen between molecules, like in an ionic bond. But the kind of forces that we're going to be referring to when we talk about covalent compounds, when we talk about these molecules, these are called van der Waals forces. Okay? Van der Waals forces, obviously named after the person who discovered them, are intermolecular forces that are somewhat weak, but still play a big part in how the molecules are going to attract to each other. And we're going to look at three van der Waals forces, the three most common. The first one is called a dispersion force. It's also sometimes called a London dispersion force, or LDF. Dispersion forces are the weakest of all these intermolecular forces. And they occur because electrons that are moving around a nucleus are going to disperse in different ways. Now, that may not mean a lot if you don't see an example. So let me draw you an example just real quick here. Let's say that we're talking about fluorine. Oh, geez. I don't know why that happens on my computer, but it does too many times. So we have a fluorine molecule, or a fluorine atom to begin with. So fluorine. Now, what do we know about fluorine? Fluorine is in group 17, so it starts off with 7 valence electrons. So I'm going to draw 7 valence electrons around here. Right? And then there's number 7. And then, of course, if there were another fluorine atom nearby, it also has 7. So they both want 8, right? So what would they do? They would share these two right here. So this one could claim, hey, I have 8 valence electrons around me. I'm pretty stable. This fluorine here would be like, hey, I have 8 valence electrons also. I'm pretty stable. Right? And those two in the middle, of course, are the ones that are being shared. That's usually what we put the dash there for. Now, when I draw a structure like this, and I have all these dots just sitting here, it looks like the dots don't go anywhere. But in real life, those are electrons. They're whizzing around really, really, really fast all the time. So if these electrons here are whizzing around here, they're not all staying in the same place. It's possible that the electrons here could move around over here, which could move back over here, and so on and so forth. And they just keep doing this whizzing back and forth. Now, what if, just for a moment, all of those extra electrons that were there all happen to end up on this end of the molecule? Just for a moment. Well, there would be a lot of negatives on this end. And so just for a moment, this end of the molecule would be partially negative, and that means there's not many electrons over here. So this side would be partially positive. Now, it doesn't stay that way, because remember, the electrons are just constantly whizzing around. So this might have occurred for just an instant and then disappeared as the electrons moved on their way and kept moving around. Well, what if there was another fluorine molecule right nearby? Right? It was doing the same thing. Now, first of all, would we call a fluorine molecule polar? I mean, is there a difference in electronegativities between F and F? No. I don't care what the electronegativity of F is. If you subtract it from another F, you're going to get a difference of 0. And if we have a difference in electronegativities of 0, that's a nonpolar bond. So this is a nonpolar molecule. There's no partial positive or partial negative that normally forms. But again, these electrons can whiz around all the time. And if they're doing that over and over and over again, it's possible that you might get a whole bunch of them for just an instant to show up on one side of the molecule, which would make that side, just for an instant, partially negative. And so that means there could be just a slight attraction that occurs between these two right here. That's what we call a dispersion force. Okay? It's very weak. It doesn't last. Like I said, this lasts for an instant, and then it's gone. And then there's nothing to hold them together again. So dispersion forces are generally only forces that we talk about with nonpolar molecules. That's the key. Okay? Nonpolar molecules don't have partial positives and partial negatives normally. So the only time that they would ever attract to each other would be through these dispersion forces. Now, the next step up from a dispersion force is called a dipole force, or a dipole interaction. And this is where you would have polar molecules. So now we're talking about molecules that do have a permanently partial positive and a permanently partial negative that's already there because they have polar molecules. In this case, right, now we have something that's a little stronger than a dispersion force. So what would that look like? Let me give you an example of NF3. Okay, so NF3 would look something like this. That's really bad, but you get the idea. And going away from us, right? And then each of these F's has lone pairs around it. So this is what an NF3 looks like. Now, if I looked up the electronegativity of N and the electronegativity of F, the difference between those is greater than 0.4. In fact, F is the most electronegative element in the entire periodic table. So it pulls on the electrons away from the nitrogen toward the fluorines. So what does that mean? That means the fluorines are going to become partially negative, and the nitrogen would become partially positive. Now, is there a difference between the ends of this molecule? The top of the molecule is partially positive. The bottom of the molecule is partially negative. So there is a difference. This is a polar molecule, right? These partial positives and partial negatives are not just going to stay here for an instant and then leave. They are permanently there because the fluorine is permanently pulling on those electrons harder than the nitrogen is. Now, what if there is another NF3 right nearby? And this N is also going to be permanently partially positive. Well, now there's an attraction that occurs right here, right? That's going to hold this together. That's called a dipole force or a dipole interaction. That's going to hold those NF3 molecules together, a little bit stronger than dispersion. And a little bit stronger than that is something we call a hydrogen bond, although it's not a true bond, so don't let the name fool you. It's still just an intermolecular force, but it happens to be an especially strong one because it occurs between a very electronegative element, like O or N or F, and hydrogen. Okay, so what would that look like? Well, water is a great example of this. So we know that water is a polar molecule. The oxygen here likes to pull on these electrons and become partially negative, and that leaves the hydrogens partially positive. What if there were another water molecule nearby? Same deal. This water molecule also has a partially negative oxygen end and a partially positive hydrogen end. Well, there's going to be an attraction that occurs between the hydrogen and oxygen between these two. And since oxygen is very electronegative and hydrogen is not, there is a big difference in electronegativities. Even though they're in separate molecules, there's a big difference in electronegativities between those two. And so there is an attraction that we call a hydrogen bond. It's an especially strong intermolecular force. That means that water molecules are very sticky to each other, right? They're very attracted to each other. This is why water, in many cases, is a liquid. Why is it a liquid? Because it's being held together and doesn't separate very easily. What does it take to turn water into a gas? Well, think about it. If you're at your house and you wanted to turn water into a gas, you would probably have to put it into a pan or something like that, put it on your stove, and give it a whole bunch of heat before it would boil away into steam, into a gas. And you know why you'd have to put that much energy into it? Because you have to break all of these hydrogen bonds that are holding the water molecules together. Okay? So that makes water actually kind of unique because there's not a ton of substances out there that have hydrogen bonds. And so that makes water especially sticky to itself. All right? So again, these are the three that you need to be aware of. Dispersion forces, which are the weakest ones. They only occur basically in nonpolar molecules. Dipole forces, which occur in polar molecules, but there's no hydrogen there. Or hydrogen bonding, which occurs in polar molecules that have a really electronegative element, like O or N or F, and hydrogen. Okay? Those are our three choices for intermolecular forces that exist out there. And then what that does, it affects the properties of the actual substance. So here's sort of a summary of everything that we've talked about now with ionic and molecular compounds. So ionic compounds, that was back in chapter 7. We said that if it was ionic, that means that the metal becomes positive, the nonmetal becomes negative, and they're being held together because of their positives and negatives. Those are ionic bonds. That's where there's transfers of electrons. Somebody's taking the electrons. There's no sharing that's occurring here. So it's always a metal and a nonmetal. These are always solids at room temperature because they're being held together with such strong bonds. But molecular compounds, they're made up of just nonmetals and nonmetals. They just share electrons with each other. Not always equal sharing, but they always share electrons. So how do you know whether they're going to be solid, liquids, or gases? It totally depends on their intermolecular forces. Generally, if we're talking about something like just dispersion forces, then you're probably talking about something that's just a gas, maybe a liquid. But if you've got something that is a dipole force or hydrogen bonding, now you're talking about something that's a liquid, possibly even a solid. Okay? So that's going to be some of the big differences. In fact, the differences between these two compounds is important for you to note. This is also in your book. As you can see, this is table 8.5 in your book also. Okay? All right, that's it for covalent compounds. You should be able to draw Lewis structures, determine shapes. We should be able to determine polarities and intermolecular forces.